So we went through and looked at the citric acid cycle, or really just one step within the citric acid cycle. Oh, excuse me. We discussed that we needed to make sure that we address the question that's asked. So we aren't just trying to make a positive cell potential. In this particular case, what we're trying to do is exactly what the reaction says it is. So when we go through and run this reaction and we do all the calculations, we ended up with a cell potential that was negative. And as a negative cell potential, what does that mean? It's a non-spontaneous reaction. So if we consider this chemical reaction, it would not go forward on its own. Generally speaking, that's a good thing, because if we're considering biological systems, while we want the Krebs cycle to run, we want it to run when we want it to run, or when our cells need that reaction to run. We don't want it to be constantly running and generating products. Okay, so if we consider most biological systems, most of them are probably not going to be spontaneous. Okay, which means we have to have something in place to force them to occur. And that's where we advance to our next slide. Come on. Did I do it? I didn't do it. I did do it. And they added in some extra context. 37 degrees Celsius. Why 37 degrees? Anybody know that temperature? No nurses? Doctors? That's body temperature. Okay, so if we modify our reaction to run out of non-standard conditions, i.e. in a biological system, pH is 7, because that's pretty standard for our internal systems. Okay, and then provided the ratio of our NAD plus to NADH, and supplied some extra information, the concentrations of malate and oxaloacetate. So a whole slew of extra information. This extra information ultimately leads us to use what equation? I know you're not responsible for naming things, but this is your Nernst equation, right, which I'm probably going to butcher, but our non-standard cell potential is our standard cell potential plus? Minus, of course. RT over, whoops, got excited, over NF times the natural log of Q. Okay, that Q is where all those concentrations come into play, our non-standard conditions. And when we run this calculation, what happened to our cell potential? Became positive. So our reaction is now spontaneous. Sign-in sheets. I think you missed that, right? Okay. So in a biological system, what can happen? Come on, please work with me. I want to go faster. The concentrations of our individual reactants and products are very tightly regulated within individual parts of the cell, depending on what each of those parts of the cell are trying to go through and do. So if we look at NAD plus and NADH, those are our reactant product for our oxidizing, reducing agents. You can figure out which one's which based off looking at chemical equations. Okay? And depending on where you're at, we're going to have a very tightly regulated system or imbalance of those things. Okay? Why? Because what we're trying to do is control those chemical reactions. And we want the balance of those reagents to come into play in a certain scenario to allow certain chemical reactions to go forwards. Okay? But we also don't want that to happen in all parts of the cell. Okay? So for instance, the mitochondria is the powerhouse of the cell. There we go. Okay? And that's producing tons and tons of energy, but do we want tons and tons of energy everywhere within our cell? Okay? We want that controlled. So different sections of the cell are going to have different functions, and so they're going to have different concentrations of these individual reagents within that system, and that's going to control the cell potentials occurring, different cell potentials. Kind of make sense? Just kind of a really neat system if you really think about it, how it's all organized and stacked to allow these chemical reactions to happen. Now we're going to kind of move into some slides that I think I'm going to shift around for Monday. But we've got the history of the battery. We've got some information about battery technology and why we'd want to go through and do it. Okay, we've got some examples on how we could go through and run a cell potential, okay, or calculate this. We have done this kind of example before. And so we'll save it and kick it for Monday as more practice before the quiz. more stuff on cell potentials and different types of batteries, particularly now moving into our lithium batteries, okay? And then how we'd recharge it, all that kind of fun stuff. Some information about how battery, I feel really bad that we're just whipping through this, just for the record. I just needed to say that. Okay, how our costs of batteries start dropping off as our technology improves. Okay, and then we can start to see the sales of battery cars and all of this over time, yada, yada, exciting stuff. Okay, where's our lithium come from? Because that's going to control how we deal with advancing technologies, is we need to know where this material is. Okay, and if that material that we're using to make our systems is in a system that is not easily accessible, that's going to change how we look at the global markets. For instance, you can make arguments how the US just goes out and conquers every country that has oil. Right? Why? Oil was and still is a common source of energy, so it's trying to create that energy independence as much as possible. As we change our technologies, we're going to have to change our outlooks, right, and where we're looking for things. Okay, different materials, yay, pretty pictures. Okay, which then I think takes us into the next thing. Metal elements have an electron C model. Okay, this is a little bit vague and it's not super well understood. We know that it works, but why it works and how it does is still kind of up for debate, and there's active studies in trying to figure out what makes metals metallic. What is this sea of electrons, okay, and how that functions. So if we go through and look at some of these things, they're positively charged atoms surrounded by a sea of our electrons. So if we consider what happens when our metals, when we put them into ionic bonds, they give up their electrons, okay, to the nonmetal. The nonmetal was more electronegative and takes those electrons away. Right? If we look at the metals, we could envision that in those connections, they're just like, yeah, let's just throw the electrons up because we didn't particularly want them, and now that's going to allow for this free motion of electrons, quote unquote, through the system. Right? So if we consider now conductivity, should metals conduct electricity well? Well, what was electricity? The movement of electrons. So if metals don't really have any strong affiliation with their electrons, are they going to allow electrons to move by them relatively quickly? Yeah, which means metals are great conductors of electricity. If we consider the bonding in metals, we can look at an orbital diagram, and this will become more relevant. Unfortunately, I need to read up a little bit more on how it's going to apply later on. Okay, but if we look at our metals, what we're going to end up seeing is our orbital diagram, and then we can look at breaking that down into two sections. We get what's known as the valence band. Right, this is the orbitals with all of our electrons in it, and then we get a conduction band. And when we talk about metals, the section or the distance between those two groups is very, very, very small. Okay? Which doesn't make a whole lot of sense here because you can't really see the gap between those, but we're going to talk about that gap in just a second. Okay, so what does that mean for us? That means when we look at metals, once we get electrons into that conduction band, they can free flow. We can bump electrons quickly from our valence band into our conduction band. That conduction is where we're getting current moving through. Right? Those are the empty orbitals. So if we think back to the previous slide, yes, that is what I wanted to look at. Okay? We're looking at a positively charged atom surrounded by a sea of electrons, right? So if we go back to sodium, what's happening? Sodium wants to become what charge? +1, it's a group 1 metal. So what it can do is effectively eject this electron, that 1,3s electron, into the conduction band. That's our sea of electrons. The valence band is now going to be our 2p and lower. Those are all now fully filled, super stable systems. Right? What does that mean for us? Our electrons can now pass very quickly through the conduction band, right? And there's no gap between the valence stable electrons and the conduction above it. So if one electron moves on through the conduction band, another electron can come in and stabilize and kind of counter deal with the motion of those electrons. Right? So metals tend to be really good conductors of electricity. Electricity, again, was moving our electrons. Our electrons are delocalized. Right? Delocalized becomes a term that you'll see if you have to take it in organic chemistry. It's meaning really that your electrons can move, okay, from one spot to another. Delocalized means an electron on this upper, that's your what, left? Your upper left atom can easily move all the way to the lower right atom. Okay? Some of the debate behind how electricity is actually organized is that it's not necessarily one electron moving from one spot to another spot. It's one electron coming in, bumping an electron, which bumps the next electron, which bumps the next electron, which bumps the next electron. The net result appears as if electrons have actually moved. But it's that kind of bumping action that allows for, or helps to explain the speed at which electricity moves. Because if it was just electron actual motion all the way through, we run into an issue when we look at really long distances. The electricity is moving much faster than the electron should theoretically be able to move. And it's because it's not moving, it's bumping. Okay? Nonmetals and our covalent molecules tend to be very poor conductors of electricity. Really relatively high electronegativity, so when you compare them back to your metals, the electronegativity of your nonmetals is much, much higher. And what does that mean? Well, what was electronegativity? The ability for an atom to hold bonding electrons. So if we're looking at a metal where they're all connected to each other, they don't want to hold on to their electrons. They let those free go. But if we look at nonmetals, on the other hand, they have much higher electronegativities, which means what are they doing with their electrons? They're holding them. They're preventing that motion of electrons through the system. Because they're preventing that motion of electrons, that's why we would see or reference these as non-conductors. Okay? Non-conductors are also known more appropriately as insulators. Okay? Similar words can be used in both cases. We talked about metals being delocalized electrons, and nonmetals, they're localized. The electron is stuck to an individual atom, and it does not want to move to another atom easily. Okay? Can it? Yeah, absolutely. You can always force things to happen. It's just a question of how much energy you have to put in to do that. And so what we're looking at is their kind of steady states for the most part. When we look at the bonding in nonmetals, they get a little bit more complicated. So when we look at the conduction band versus the valence band, there's what's known as a band gap. Remember I said there was a gap between them that wasn't super obvious? Ta-da, here it is. The gap becomes very, very apparent in nonmetals. Right? What is this kind of correlated to? Their electronegativity. Right? If my element, carbon, is very electronegative, what is it doing to those electrons? It's holding them, it's keeping them localized into the valence system. Right? It is preventing them from going into the sea of electrons, or conduction band. Right? The ability or the size of that band gap has a lot to do with the ability of that individual atom to hold those electrons. Okay? So our electronegativity. Okay? And that's where we then correlate to nonmetals versus metals. The nonmetals have a large band gap. Because they have a large band gap, they never make electrons up into the conduction band. And if electrons can't make it through the conduction band, you don't get movement of electrons. The movement of electrons has to happen through that conduction section. That's why we call it the conduction band. Kind of, sort of? Okay. Well, then what happens? Are we just have metals and nonmetals? What else do we have? We have our metalloids or our semi-metals. Whoops, not quite yet. So here it's bringing the two together so that you can go through and see what's happening within them. All right. In metals, we can promote electrons from our valence band into the conduction band really easily. Once our electrons are in the conduction band, think of that as our free movement. Now they can run. Okay, that's where we get electricity. When we look at nonmetals, to be able to promote into the conduction band is not an easy task. Right? Because that's not easy, we tend to not see electrical conductivity. which then, come on now, sets us up for the semiconductors. What's happening within the semiconductors is they're straddling kind of both worlds. A little bit of the conduction or the metal world and a little bit of the non-metal world, which ultimately means that band gap shrinks. Right? And we leverage that to do a whole bunch of different things with our semiconductors. Right? So different materials show that band gap being small enough that we can promote electrons. It does require a little bit of energy, okay, but the amount of energy is relatively minimal in comparison to the nonmetals. Right? It's also enough energy that the electrons don't just chunk straight through. So we can control whether electrons move or not. Why would that be useful?
Electronics, circuits.
Everything to do with circuits. Okay? Think about your computers, data. If we're looking at an electron being excited into a conduction band, we could count that as a 1. It's now electron being able to move. If the electrons can't move, we could count that as a 0. And we now have 2 bits of code. We have a 0 and a 1, also known as binary. Okay? And we could now leverage the ability for us to control whether we're conducting electrons or not as a binary coding system, a switching system that would allow us to navigate all sorts of different systems, both within computer programming as well as actual hardwired electrical circuits. Okay? So that's a pretty neat system. That happens to happen really well with our semiconductors, which do tend to be our metalloids or fall on that line. And so the classic example is silicon. So we can look at silicon's electron configuration, and you might say that that looks pretty similar to the carbon electron configuration, right? Doesn't it? Why is carbon acting as a nonmetal, but silicon acting as a metalloid? What's different?
Valence electrons on silicon are at the 3p level, so they're farther out.
Why should that matter?
They're not held as tight.
Right? If you go back and look at electron configurations all the way back to 151, where your electrons exist, they are existing in these orbitals. But one of the things that this diagram does not show very well is what happens to the distance between your energy levels as you go up. They get smaller and smaller and smaller. So if we're looking at the distance between, say, the 2p and the 3s, that's a relatively large jump. If we look at the 3p to the 4s, same idea of a jump, p to s, p to s. What we're going to find is that distance is significantly smaller. Okay? It's crunched down. What does that mean? Now the ability to jump from the 3p to that empty 4s is relatively easy. That requires a smaller amount of energy, and I can cause that pop or that jump upwards. Right? That's one of our primary contributors for that band gap explanation, or one of our contributors for that band gap. Silicon just happens to hit that sweet spot real early on that allows us to have that ability to jump up in electrons. That's kind of neat. Okay? Which then gets us to allegedly what I guess today is, and we'll talk a little bit about LEDs and solar panels. Okay? Most of those are coming back to the idea of a semiconductor. Okay? And we could play around with that a little bit. What does an LED do?
Light up.
Provides light. So to get light, what had to happen? What's that? Electrons? Yeah?
Electrons move around.
Electrons move around, but I get electrons moving around in a wire and I don't get light. Why do LEDs cause it? When we look at an LED, We're putting a load on it. We're pushing electrons into that system. Where are those electrons going to go? They're going to go into our LED, into the conduction band. They can't go into the valence band because the valence band is full. They go into the conduction band. They're now in a high energy state. Do electrons want to be in a high energy state? What do? They drop in energy. As they drop in energy, that loss of energy has to go somewhere. Where does it go? That's light. Okay? That's the emission of light. So if you go back and look at your emission spectrum, again, all the way back to 151, similar process is happening within those systems. Here we're controlling it in a semiconductor because the gap between those, conduction band and valence band, is allowing us to manipulate that. Okay? What color light's going to come out? How would we determine that? They're just like, oh, it's white. LEDs are white. No, actually, most LEDs are not. But I see white. Just because you see white doesn't make it white. We go outside and say, oh, it's white light. But when it starts to rain, what do we get? A rainbow. And the rainbow shows that white light was full of colors. Same thing is happening with our LEDs. What light is going to come out of our LED? A color that matches what? The color is tied to wavelength, yeah? Bingo, there it is. The light that we get matches the energy of the band gap. That's the color light we're going to get from our individual LED. Right, why are we seeing white? Depends on the design of the individual LED systems, but some LEDs aren't white, they're red, green, and blue LEDs. And when all three of those shine at the same time, you see white. Okay? The other way to run it is that you do it similar to what a fluorescent light does. Okay? The band gap is a large enough energy that there's a phosphor, a secondary molecule in the tube, and the LED emits this high energy particle that hits the phosphor. The phosphor provides the light. Okay? So depending on the design of your LED, you're going to get different systems for how that light's being produced. Okay? And it's all coming down to that band gap. That band gap is the energy that we're referencing when we talk about these things. Okay? How do solar panels work? I knew there was another part I needed this picture for. What's the point of a solar panel? To produce electricity. So instead of putting the load into the conduction band, which we're doing with the LED, what are we doing instead? We're allowing sunshine to come in and do what to the electrons in our valence band? Excite them. Once they're up into the conduction bands, they can now freely move, and now we can put a load on the system to pull that electricity out. Right? Exact same thing, but it's all going to come down to where you're shuttling your electrons. In the LED, you're putting the electrons in, and the light, or what's the other thing? Solar panel. The solar panel, we're allowing light to eject our electrons upwards. So depending on what we want, we're going to get a different system or different manipulation of that system. Does this mean you can use LEDs as solar panels? No, not really. They're similar materials, but those materials have distinct characteristics behind them that allow them to do very targeted things. Okay, so we look at our overarching thing. Again, our metals directly tied the valence band to the conduction band, which means it's real easy to promote our de-excite our electrons. Okay, there's effectively no energy jump. When we look to the non-metals, there's a massive energy jump, which means it's very hard to get our electrons up into that conduction system. The semi-metals, that gap between those two sections shrinks. Not so much that the electrons immediately jump back and forth and we get full conduction, okay? But not so large of a gap that we can't promote the electrons. So they're hitting in this magic sweet spot that allows us to manipulate how we're putting that load on. And that's ultimately going to come down to how much electricity we want to put in versus out. Okay. Could we use nonmetals to absorb sunlight? Or let's try it this way. Could we use nonmetals to absorb energy? Sure, they could absorb energy and jump into that conduction band to allow that. The problem with that is, what's the energy? Not low. For nonmetals, it's very, very, very high. It's so high that we don't have an easily accessible natural source of that energy, so it defeats the purpose of trying to do that. What we can try and do is manipulate the materials of the nonmetal to try to force that band gap to get smaller and smaller. And if we can get it to be smaller, then maybe we can bring it into a range that allows us to actually leverage that energy that we have around us. Kind of, sort of? Okay. I keep dreading every time I touch this button. Okay, not yet. So our electronegativity between our metals and our nonmetals is our primary differential. The big deal that we care about for our semiconductors is right along that line, okay, our semimetals. Okay, those semimetals and metalloids are kind of our characteristic ones that allow for conductivity, right, or the band gap matching for our conductivity. Electronegativity is very, very high on the right-hand side, very low on the left-hand side, and we're really kind of mitigating or controlling those differences to set us up into a system that falls along that shrinking band gap line. We want a band gap that's small enough that we can allow for promotion or demotion, if you will, but we also don't want it so large that it's too hard to make that jump. Hard. The other one was easy. We don't want it to be so easy that it just does it on its own. Okay? The whole point is control. Wow, isn't that a fun lesson? So let's rank the following elements from smallest to largest energy band gap. All right, so talk at your tables. See if you can figure this out. We've got some context behind this. This, I would argue, is the most straightforward question. I can actually answer this one. I think it's the next slide or two that I'm going to run into some problems. But see if you can come up with your band gaps for these. So if you were anything like me when you first saw this slide, you might have hyperventilated a little bit and panicked, but it's not that challenging, at least yet. Okay? So if we're talking about that band gap, we aren't trying to quantify what the band gap is. We're just trying to explain relative band gaps. That's it. Okay? So don't try and make it harder than that. So if we go backwards, if we go back to this system, this helps to give us that explanation that we need. Our metals conduct electricity. What's our band gap there? Small. Okay? Effectively 0. And our semi-metals, that's a challenging one because it's not too small, it's not too big. It exists. That's about all we know. What's going on in our non-metal? It's really, really large. Right? Because the non-metal insulates. It prevents the conductivity of electrons because we can't stabilize that balancing or bouncing of electrons around. So when we go back to our question, really all we're being asked to do is to identify our metals and non-metals, and technically metalloids. So iron is a metal. Phosphorus is a non-metal. Gallium is metalloid. It's sitting right on that line. So iron is going to have the largest band gap, okay, followed by gallium, followed by phosphorus. Whoops, other way around. Sorry. Make sense? That's what we're going to manipulate as we deal with that system. Questions? Okay. So why is silicon used in semiconductors? Right, so it is all over it, and the primary, or one of the things that we would look at is the 4 valence electrons. When we go through and look at your 4 valence electrons, you're going to have half-filled valence orbitals. Those half-filled valence orbitals are a large part of what's happening in combination with the balance of electronegativity, metallic characteristics that are allowing it to either accept electrons in or to eject electrons out. That's kind of our primary system, and silicon happens to fall pretty much right at that sweet spot. Okay? So if we go through and evaluate, you can see that silicon's used in a whole bunch of different things, and it's our kind of blend between electronegativity and the ability to bond things. As we then try and go through and find other materials, we might want to branch out to find other things. Why? If we're only looking at silicon, what's our band gap? It's singular. We get one band gap. That's it. We would have to match that band gap for all of our purposes. So if we're talking about our LEDs, where we had red, blue, green LEDs, that's not going to happen, because red, blue, green are all different energies, and those energies correspond to the band gap. And so if we only have silicon as our potential semiconductor, that becomes really hard to play with the band gap. And that's going to limit what situations we can use. So what we start to do is reach out to find other materials and say, how can these other materials also act as semiconductors? Right? This is the question I'm dreading, by the way. Right? So when we go through and evaluate this, what you'll start to hear when we talk about semiconductors is different names associated with them. Right? So for instance, gallium arsenide is a semiconductor. Right out of the gate. Okay, so what's special about gallium arsenide? Why would it allow to act as a semiconductor? Did you read the background material? Damn it. See? One of you was supposed to have done that. And been like, this is the reason why. Right? And unfortunately, I haven't had time to read it, and so I'm stuck kind of in a hole on this one. This is a question that I tried to run by my wife to go through and say, hey, I need help, tell me what's going on with this. And pretty much all she spit out was facts. As in, 3-5 are semiconductors. What do we mean by 3-5? Where's gallium? The third. And, I already forgot it, arsenide? 5. Right? So 3-5 materials are semiconductors. Right? So we could go through and look at these varying elements and say which of these match that 3-5 scenario. If they match, we're now looking at something that could be a semiconductor. Right? So gallium selenide isn't a 3-5, that's now a 3-6. Indium phosphide, 3-5. So indium phosphide is going to match that system. Cadmium sulfide, where's cadmium? All the way over here, and sulfide all the way up there. I believe the pattern that we're going to get, so if we look at cadmium, that moves way outside of our realms. I believe the pattern that we're going to get is that when you look at the averaging between this, you're falling onto the metalloids. Right? So 3-5, if you look at the valence electrons with how they align out, you're going to get a sequence that effectively matches, for all intents and purposes, the silicon valence shell. Right? Why does that become important? Well, one of the things that my wife said at the end, well, it's not just 3-5 materials. There's also other semiconductors, like 6-6. Well, how would 6-6 work? So 3-5 gets us 8. 8 electrons is matching, because we're looking at 2 elements. Actually, there are 4 electrons. 6-6, it's going to set us up with 12. And I think that's going to fall back to, when you look at how the orbitals fill out, the same deal, 4 electrons, just like the silicon. Right? That, unfortunately, is one I cannot answer well yet. I'm just aware of those random facts at this point, and I need to do more reading to make sure that we're covered on that. Okay? But at that same time, we've got to try and move through some of this content. Make sense? as much as it can. Okay. So how does an LED light work? We already briefly talked about it. Our energy is being supplied by a battery, dropping our electrons into that valence band, or exciting our electrons from our valence band into the conduction band. When they relax back down, that's our light emission. Okay? The amount or the color of light that we're seeing is due to that band gap. And since we're talking about color, this is no longer as simple as just, I need ones and zeros for binary code. I now actually need to match the band gap to match the color that I want to see. Okay? That means I have to tune the material. I have to change the composition of what's going in so that I can change the energy of that band gap to match whatever color I want emitted out. That becomes an important distinction and differentiation between this. So our LEDs pretty much right away bust the whole, let's just have semiconductors and be excited about it. Okay? Now we actually want to tune much more precisely what's going on within it to ensure that we can get the colors that we want. What button? Okay? More stuff that is, again, outside my wheelhouse, but we're going to take a look at it anyway. It's a blue box, so officially it's not my responsibility, right? Size of the energy band gap depends on the identity and composition of the elements. This is what we were talking about. As we change the composition of those elements, we're going to change the energy of that gap. So what we've got here is a variety of coupled materials, or 3 different materials. We've got silicon carbide, gallium phosphide, and gallium arsenide. We can see their energy band gap represented in joules. We can talk about the wavelength of light, and we can talk about the color that comes out of it. So what we want to look for here is potential trends that you notice within that system that might help you navigate them. Does that kind of make sense? So take a look at the materials, take a look at those energies, and see what trends you notice, if you notice anything. So, in looking at that observation, is that an observation from this semester, or is that an observation for a different semester? Yeah. That's a trend, though. So level up. Sign-in sheet, did everybody get it? Full disclosure, I totally cheated on this because there's an answer written. Oh, I should have paused the lecture. Oh, well. There's an answer actually written. If you have the PowerPoint slides in front of you, you can actually look at the footnotes behind it. So what do we see? One observation that I'll point out so that we don't get this one. Okay, as you can see, oh, well, there's a comparison between the energy and the wavelength, right? Right, the smaller the energy number, so right, this is smaller, and this one is larger. We change the wavelength, so a larger band gap resulted in a smaller wavelength, and a smaller band gap resulted, and I didn't give anything away, resulted in a larger wavelength. Right? Perfectly legitimate observation. I love that. That's fantastic. Is that observation from this semester? No, it's 151. Okay, that's going back and looking at the wavelength of light, wave nature of light, and showing the relationship between energy and wavelength. So that's legitimate, but what we want to try and do is bring in how our elements are changing, ultimately, these numbers. Right? So what do we see changing within the elements? So we can push on electronegativity. Electronegativity. So higher electronegativity meant what? Higher electronegativity was a larger band gap. Bad gap. Come on now. Okay, do we actually see that?
Yeah.
Silicon, copper, not copper, you know what I meant. Carbon, thank you, right, are much higher on the periodic table. Higher is more electronegative. If we take a look, what was the gallium phosphide? Gallium phosphide, we're starting to get a little bit lower on the periodic table, and then our gallium arsenide even lower still. Right? So as we increase the electronegativity, we're seeing an increase in the band gap. Does that make sense?
Yeah.
Why?
Because the bigger the band gap, the more energy you need to excite the electrons.
True. Bigger band gap means more energy. Yes.
Yeah.
What does that have to do with electronegativity?
The lower the bigger the electronegativity, the more energy.
Why?
They can move.
That goes all the way back to our properties when we looked at our band gap, our
Because
materials.
they want to hold on to electrons.
They wanted to hold the electrons. They prevented the motion of electrons, which meant we increased that band gap. So the increase in electronegativity does appear to correlate to a larger band gap. We actually saw that when we talked about nonmetals and comparative to metals. We go back to the blue and white boxes. Okay? That's what that actually showed. So that makes sense. Okay? As we talked through it, I said, because silicon was a semiconductor, but carbon was not. What was the differential there? Why was silicon allowed to conduct but not carbon? What could silicon do that carbon couldn't?
Hold on.
So we could look at electronegativity, but what else was the difference? Had to do with the electron configuration. They have the same overarching configuration, but carbon, if we look at carbon's valence band, was looking at the 2p, the next jump up to our empty orbitals was 3s. For silicon, it was 3p to 4s, and what did we say happened to the distance between those? They got smaller. So the larger the element is, the smaller the gap became between the occupied orbitals and our unoccupied orbitals. So if we look at increasing size of, what is, sorry, somebody's doing something fun on the computer over here. Increase in size did what to our band gap? Lowered the band gap. Right? So we could go through and use that information and start saying, well, what if we mix this and this? What might we predict happens to those individual band gaps? Kind of make sense? So what we're trying to pick out is those trends. Which then sets us up with doping. Okay? Doping is adding very small amounts of a different element to change the overarching properties. Okay? So it's going to enhance your conductivity in some form or another. So you can get what's known as N-type doping, N for, what's up there? Negative. So you're adding an element that has more valence electrons than your bulk material. If there's more electrons there, that's going to change its ability to conduct your electrons. Right? So we've got a picture here. If we've got more electrons in that valence band, you're going to start to populate electrons a little bit higher up. Right? And if we look at p-type, you're starting to create holes now in your valence band. Right? That will modify that band gap and change how we would manipulate the end systems. And yet, again, another freaking question, but hey, you know, not everything can be a win. So if we go through and look at silicon-based semiconductor, which of these elements could you use for N-type doping? Which could you use for P-type doping? Actually, I think this one's fairly straightforward. Okay, so remember your N-type, you're adding an element with more valence electrons. For P-type, you're adding an element with fewer valence electrons. So if we're looking at a core material as silicon, where did it go? There it is. Right? How many valence electrons does our silicon have? We have 4 valence electrons. If we're going to do N-type doping, an N-type is an element that has more. So I need anything with more than 4 valence electrons. Said another way, as one of your colleagues pointed out, anything to the right of silicon is going to have more electrons or more valence electrons than our silicon. And if we're going to do a P-type doping, we want an element with fewer, so we want something with less than 4. So anything to the left of silicon. When we say to the left and right, are we only talking about left being aluminum and right being phosphorus, sulfur, chlorine, argon? Nope, we're talking about anything. So if you just draw a line, anything up, down, just to the right and left. All right, so talk at your tables, see what you can come up with identifying those. I would argue this question sets you up to kind of get confused right away. Okay, why is that? Because as soon as it starts off, the very first thing it gives you is GE. Is GE to the left or right? It's directly underneath. Does it have more or less? No, which means it's not going to work as a dopant. Okay. Where is SB, antimony? Was it to the right?
Yeah.
Oh yeah, it totally is. Never mind. Okay. To the right means it was greater than. So we're looking at an N-type dopant. Where's the gallium? To the left, which means we're looking at a P-type and indium. Left, we're looking at a P-type dopant. Okay. What we're not discussing here is how all this gets done. Okay. How all of this gets done would be discussed if you were going to move into a material science degree. So if you were interested in that path, really cool stuff can happen there, and you talk about how you would grow these materials. And yes, it is a growing process. So diodes, we can now talk about things that I almost guarantee a significant portion of this class knows more than me about, because we're moving into electrical engineering. So diode is made from an N-type and a P-type semiconductors put together, right? Because you're now looking at how that electric load is going to generate light through that system, right? You're putting electrons up into that conduction band of your N-type. Those electrons will shuttle across to your P-type hole and then drop in energy back down to the valence band and then continue your loop. Okay, that process is going to see, since you're seeing a drop in energy, is how you're seeing the light emission. Kind of make sense? Okay, so LEDs are much more energy efficient. We don't waste a lot of energy as heat. They still heat up, and that heat does modify the band gap slightly. And so as they get hotter and hotter, they start to become less and less efficient, which is why if you've seen LEDs or large LEDs, they tend to be for lights and things like that. You'll notice a whole bunch of fins on them. What are those fins?
Heat sink.
They're heat sinks. Okay, it's to help dissipate some of that heat so that they can actually maintain their efficiency. Okay, so while heat is a problem for them, it's not as much as a problem for them as a normal those are incandescents, right? An incandescent bulb, and you would know that if you ever tried to unscrew an incandescent bulb after it had been plugged in for a while, because it will burn the bejesus out of your fingers. Okay, whereas the LEDs won't burn your hand, they do just lose some of that efficiency. Okay, they are a pretty recent invention, and so we're still manipulating and trying to figure that out. And we can look at phasing out costs of LEDs and all of that. If we go through and look at semiconductors and solar cells, okay, a photovoltaic solar cell is the opposite of an LED, okay, because the whole point of the LED is that we put a load on it and light goes out. We don't want light going out, we want light coming in. As the light comes in, it's going to force the electric current effectively going the opposite direction through the system. So we would align your N-type and P-type semiconductors slightly differently so that when light comes in, you excite your electrons, and those electrons can then move through your system. Okay? That energy theoretically can be stored for later use, or you have a load on it instantly. Okay? Which I don't know enough about, but I have heard someone talk about it. If we consider our electricity usage, our power plants are constantly on and constantly producing energy. That's the only way we get electric flow, is they're actually producing energy, and it has to get consumed as it is produced. If they stop producing, our lights go off. If we stop using it, there now becomes this excess buildup that causes problems within the power plant, so they have to stop producing it. So they have to cycle the power to match the consumption need. Right? How can we mitigate some of that? Batteries. Okay? You can insert batteries into that system that would absorb some of the excess energy being produced by the power plants that wasn't being consumed, and then when the consumption kicks back up, you can start to deload your batteries. So even when we talk about solar cells, like if you have solar cells on your roof, it's usually a good idea to consume as much as you possibly can, because you don't want to sell that back because you're not selling it back at a profit. Okay, that sucks. Okay, so maximize your load if you've got solar cells. Or throw in batteries. Batteries also, my low battery. Or throw in batteries, but batteries add another cost behind it too. Thank you for the heads up. Okay, but this device shouldn't break down. So where does our silicon come from? Okay, the silicon is typically coming from sand, and we react that in the presence of carbon to produce pure silicon and carbon monoxide. Okay, we need pure silicon for this to create our optimal band gap systems. If we don't have that pure silicon, we're not going to get the proper conductivity that we need, or the unconductivity, depending on how you wanted to look at that, to allow that system to function. So now I think we're outside of content and we're just into a bunch of extra information. Worldwide, about 4% of our total energy currently comes from solar. Fun random story, I just happened to walk into the mother of one of my daughter's friends, and they just moved over from Germany, and they were saying they were really shocked at looking at all the rooftops in Arizona. They're like, where we're from in Germany, every roof has a solar cell on it. Every roof has a solar cell producing energy, and we get sun like 2 days out of the year. And then we come here where there's sun everywhere and nobody has any solar cells. We just don't get it. Okay? But I think that's a pretty popular consensus from the national, global world, is that they just don't understand what's happening in America.
I was about to explain, like, there is an entire, like, almost monopoly on solar cells because all the big power companies, like, actually actively trying to undermine that and get the point.
Oh, I'm aware of it because when we put solar cells on our roof, we was like, oh, cool, we could sell it back. You don't sell jack back.
No, they also like increase the price so you never actually buy them.
Yeah.
I get that's a big difference.
Yeah. You gotta love capitalism when it comes to bite you. Capitalism great is when it does good things for you. It also can come in and ruin you. So cost of solar energy has decreased dramatically. Why would it decrease? Why do you think it's decreasing?
Getting more efficient to use it.
Becoming more efficient. We're getting better at collecting the materials necessary to build those systems. Okay, we're starting to actually build the infrastructure to allow us to actually use that technology. That infrastructure wasn't there not all that long ago, and so we're starting to see a dramatic decrease in that price. Okay, what would I think would be fun to include on this would be what's the price that you're producing electricity-wise from solar cells versus coal or gasoline that you're buying from, not gasoline, but oil that you're buying from your power plants. Because while this shows a very sharp drop, I think if you look at the price of electricity produced by our power plants, it's significantly underneath this, or undercutting it the whole time, which is really unfortunate. Price of electricity from new power plants, so you can look at how the cost of electricity has declined. Price of electricity from solar has declined by 89% in those 10 years, which makes sense because if we have more of the technology and it's cheaper to produce it, it's going to be a dramatic decrease in the cost to an individual user producing it. 30% of the world's energy currently comes from renewables. Okay? So that's a really depressing plot to look at, but there we go. Whoops. Renewable energy is powered by chemists, or powered by chemistry in general. So if we can go through and look at the importance to energy versus the supply risk. So this is an interesting plot. You're looking at the individual materials used for renewable energy. Okay, so for instance, solar cells, we need silicon. So where are we getting silicon from? Okay, so you can look at how those different materials, where they're at and how they exist and how important they are to our overall process that we're running through when we consider energy consumption. Okay, so that's kind of a neat one, I thought. So if we look at supply risk, what kind of systems do we have in place to actually obtain the materials, the raw materials to do the technology we need? If we're looking at a high risk, that's going to be kind of problematic. Okay? If we look at how important it is, okay, if it's really, really important, that's also going to be potentially problematic if it's a high risk. So if we look at that upper right-hand corner, all of those elements become very, very important and highly valuable to our energy production. Okay, so if you were looking at this from a political stance, what you might then go through and do is say, well, we need to make security arrangements to ensure that we have a constant supply of those individual materials. Okay? So you're repositioning chemistry now in a political sense to ensure constant advancement. Okay? More people care about climate change than you might think. So this is just going through and showing where we're at kind of politically within that system. So despite what we may hear from certain circles, allegedly the statistics are showing that the majority of people are concerned about climate change and global warming, and that we should try and come up with systems to go through and fix it, right, or to address. This one goes through and points out that people of color, particularly women of color, are the most alarmed. So you can go through and think about where there are reference how they're pulling all this information to then point out, and why would they point this out? Different questions, repackage how we look at this. Why does this become a useful thing to point out? So we could try it a different way. When I ask a question, how many people respond? Wow, see, it works. Okay, we get very minimal response. Okay, and if I now go and push individuals and say, why are you not responding in class? Why are you not volunteering answers? Why are you not asking questions? Any guesses as to what one of the number one responses is?
I don't know.
That's actually not the answer, and you
Really?
actually spoke up. Yeah, it's generally not that I don't know. It's a derivation of that potentially. I might be wrong, okay? I don't want to be the only person. I feel like everybody else knows what's going on in this class and I'm an idiot, okay? It's totally my fault. The point of showing statistics like this is to try and show you that you're not alone. There's lots of people that support that, and it's trying to bring kind of more people to the forefront to recognize, hey, you should actually be speaking up, okay? You need to be more of an active participant, both within global warming and I would argue within classes. It's a bit late now, at least for this class, okay? But that contribution, you are not alone. If you have a question, I guarantee you at least 2 or 3 other people in the class have that same question, okay? And we're in a small class. Are you planning on transferring to, I don't know, ASU, U of A? All of their class sizes are significantly larger. You're going to look at an even larger population of people that also need that help. One of the biggest things that you can do to advance both your academic and career choices is to ask questions, is to start that conversation to get content moving forward. The longer you hold your tongue and try and fight through something on your own, the longer it actually takes you to achieve that goal. So the more you can speak up, the better your chances are for success. Okay? We did a poll at ASU in grad school, okay, for all the people that had gotten PhDs that year. And we asked, what's the number one piece of advice you can give PhD students continuing to move up or trying to get their degrees? Their number one piece of advice was to ask questions. The instant they realized that they could ask people for help, they actually started making progress on their PhDs. Okay? So if you start to become more active and ask and build those questions, okay, you'll start to understand the content better and you'll start to advance through whatever you're working on more efficiently and effectively than you were in the past. Okay? So these kind of surveys are trying to point out that you're not alone. There's lots of other people that have similar concerns. Start voicing those concerns. Start bringing them forwards. Okay? Where are we at? 40 minutes. I think we're starting to move into, I'm going to pause the lecture recording for a second. So, in coming back, we'll go ahead and start off with apologies. This is the history of the battery. Neat. Next. So, battery technology. We talked a little bit about our battery technology. This helps to minimize the production of CO2. So, our rechargeable batteries can be used over and over again, and they're more sustainable than if we're looking at standard batteries. Okay? As long as we continue to use them, okay, that's where they become powerful. You will hear reference sometimes to lead-acid batteries. Lead-acid batteries are one of the best exchanges of batteries that we've got because we've built an infrastructure around recycling and repurposing those materials. But if you look at your standard AA batteries, we don't do a real good job of those. And so that would be one of those things we would want to improve. Okay? So where we'll move to here is that we're going to take a look at a lithium-ion battery, and we want to write out the spontaneous overall reaction and calculate the cell potential. Once you've got your cell potential, we want to identify the anode and the cathode so that you've now got those. So we're now doubling back to our voltaic cells, and we're starting in with some more practice. This will probably be where we end, is with this practice. So go ahead, start working at your tables, get it put together. So I've added some text as an overlay behind this. Okay, these would be things that I would immediately write down as I was attempting to go through and solve. So this is not something that I'm just adding for your benefit. This is actually for my benefit. Okay? And again, as it works for me, I would argue it would work for you in the case of a quiz. So write the spontaneous overall reaction. As soon as I'm saying spontaneous, I need to identify what that means. And since I'm looking at cell potentials, which I can see with a quick scan that we're seeing cell potentials written out, that's going to mean I need an E cell that is greater than 0. Okay? Also known as a positive cell potential. Okay? Now I continue reading. Overall reaction in a lithium-ion battery and calculate the E cell. Look, I'm going to calculate the E cell. So hey, if I've done that flip or recognize what I need to do, that's going to be helpful. Okay? So then I could look at my two equations and say, well, which equation do I need to manipulate? Or do I need to manipulate anything? For me personally, again, I would go through and I would highlight and identify the arrow and my electrons so I can recognize what I was actually given. Right? I would heavily bet that you're always going to be given the reduction reaction, but I could be wrong on that. Right? That's why I would go through and identify it to make sure that I know exactly where those things are. Because these are now both in the reduction potentials, I'm not going to be able to cancel out my electrons. I have to flip one equation. Which equation do I flip? If I don't know, I could go through and just start flipping and see what happens. Okay? A couple options could come out. One, you just look at the cell potentials and you just start flipping the cell potentials. And if I flip the top one, that makes that top one negative. And if I add them up, that would be a negative. So that didn't make sense. I got to flip the bottom one. Okay? That works. Okay? The other approach was suggested by someone in the class on Tuesday. And they said that when you're given a system like this, always flip the one that has a lower cell potential. Okay? Or a more negative cell potential. Okay? Which makes sense if and only if you're looking for a spontaneous reaction. Okay? So we got to be real careful with that system, because if we go back to the biological systems, that's not necessarily the case. Okay? Since here we're looking at a battery, we're going to want to flip the one that generates that. Go ahead and ask while I try and do some writing.
Will you always preface that you're looking for a spontaneous versus non-spontaneous reaction, or will it just be like context?
I don't know how to answer that question. I don't write the
Tell us
quiz.
if it's spontaneous or not.
Will I always preference it as being spontaneous or not? I think not, technically. Right? And we've got the biological systems to explain that. Because in the biological system, we didn't say, is it spontaneous? Do the spontaneous reaction or do the non-spontaneous reaction. We said, do the reaction. Right? So what you should be following is the context clues within the question. If you're looking at a voltaic cell, you want a positive. Okay? So it makes sense for something like this. We're looking at a battery to produce electricity. We want to have the positive. Okay? It has extra emphasis saying it's spontaneous, so that makes sense. But if we move to the biological systems, okay, you may be told, is this reaction spontaneous or not? You now have to do what the reaction says, not just make it spontaneous. Does that make sense? As we continue the rest of this out, I know we're done. Lithium, cobalt, oxide, lithium plus cobalt, oxygen 2, plus our electron. What happens is our electrons cancel. I didn't flip that equation, which means that cell potential would just get rewritten. 1 volt, which then means my cell potential as my answer is 4.0 volts. You'll note within this, I'm not using any special formula. I'm just adding these things up accordingly. This isn't following the cell potential equals the reduction potential of the cathode minus the reduction potential of the anode, I think is the formula. I think that's a stupid formula. It's a really bad idea. Follow the equations. It sets you up with a more appropriate context. Okay? Our overall equation, we could then go through and add that up, but just to finish out the last little part, okay? What's happening at the anode? Well, the anode is where we gained electrons, so I could go back and look at my system. Where do my electrons? My electrons are on reactant side here, which means this bottom reaction is my reduction, which means this is what's happening at my anode. The anode is going to be the solid material in that case, so our cobalt oxide. And then the other reaction has our electrons as a product, which means that was our oxidation. That is this is why you write it down. This would be the cathode. Red cat, right? The blue one is our oxidation, which is our anox. We'd go over to our reactant. There's our anode. Everybody got it?
Yeah.
Okay. We'll do more practice like this on Monday. I think all the content is covered. I have not yet seen the quiz. We can have more of a conversation on Monday.